Hi, I'm Aaron, and today we're going to try to build a linear regression model from scratch in Python, just using base Python and Numpy. If you're like me, you might be learning or have learned some advanced, maybe it's machine learning or other generalized linear models or some other predictive techniques, all things that are involved with working with data. And again, if you're like me and you want to know the details and really understand what's going on and what you're using, one of the best ways to do that is to dive in and try to develop something on your own from scratch. I think it's one of the best ways to really learn because it focuses your attention to detail and makes you think about all of the important things that kind of might go on behind the scenes that you typically don't have to worry about. I also think once you go through that, you end up having a greater appreciation for some of the free and open tools that are out there to use and just how robust they are. So that's also a nice benefit as well. So without any other introduction, let's go ahead and try to dive into this, okay? All right, so if you're looking at this to try to build a linear regression model from scratch, it's probably not your first time hearing about linear regression. You probably have some familiarity with it already. We're going to do this with gradient descent and not ordinarily squares. And I went through ahead of time and done a lot of the details, and so I'm going to try to provide enough in this video to maybe get you through this so you can understand what you're doing and we can go ahead and code it up in Python. But I want to mention that there was a lot of details that I'm kind of skimming over here or assuming and taking for granted. And to kind of repeat myself, I like to really go into those details and understand those things because I think maybe sometimes that's where the neatest problems are or the biggest challenges are. And so I will be putting deep dive videos together. I might just record them on Twitch streaming at some point and then maybe upload them to YouTube. Who knows? By the time this is uploaded, maybe we'll have descriptions below. It ties a lot of those core classes you might have taken in college as an undergraduate together: calculus, linear algebra, statistics. It's just a really, really cool situation. So y equals mx plus b is our slope-intercept equation of a line. When we're doing a model for prediction, in this case, we're going to write it with the convention y hat equals b plus w1 x1. So y hat is your predicted label of your linear model. B we call sometimes the bias or your y-intercept. Sometimes we'll call this w sub 0 there. Wi is the weight of feature xi in there, and the slope it's also called the slope if you think about it in terms of traditional slope-intercept form, y equals mx plus b. Okay. And then xi, each of the x's there are the individual inputs or features of that. So we would have a typical data set like the price of a house and the square footage. And our goal, obviously, right, is to fit a equation of a line that goes through this as best as possible. So maybe something like that would be our linear model. In this case, it would be a simple linear regression model with just an intercept and one input feature, square foot. Okay. We'll talk more about generalizing it into the cases where you have several features there. Luckily, linear algebra handles a lot of that for us here. With the gradient descent approach, if you're coming from a traditional statistics background and haven't seen a gradient descent approach, we're going to introduce a concept called loss. And loss is a number indicating how far off the model is if the prediction or how far off the model is from a single prediction on your example. So if the model is perfect, your loss is 0. So if we go back up here, though, for example, if I look at this data point, the distance, for example, from here to the spot in the line, that could be, I could calculate that distance, and that would be the loss. And we want a way to aggregate the loss for all of our points. So we tend to use squared loss, or an L2 loss. It's a very common way of computing loss, but isn't the only one. That is the difference of the actual observation minus your prediction value squared. So in our notation above, that's y minus y hat squared there. And if we average the squared loss per example over the whole data set, we get what's called the mean square error. So that is the 1 over n, and then we have y minus the predicted value there squared, and then our summation, we're just going to sum over all pairs in our data set. So we're looking at all cases in our data set. N would be the number of cases in our data set here. So that's the mean square error. It's a pretty common loss function. And again, there are other loss functions out there. Sometimes you'll see a halved mean square error where they'll do 1 over 2n. And the only reason for that is I think later on when you get to some the calculus part, having a 2 in the denominator cancels out a 2 in the numerator. It's kind of nice, but it's still, if you can minimize loss in this fashion, you can minimize half the loss in the same way. So when it comes to calculating the loss for our simple linear equation, if we look at what we have right here, 1 over n, if we have n data points, we're going to take each of our observed values minus a predicted value, square it, and we're going to add those all together. And if we have just a simple linear equation for y hat, we can substitute in b plus wxi. And that's going to go into our equation there. So this is what our loss function looks like for a simple linear regression model. Okay, so the concept of calculating loss is one thing, but what we really use that for is as a measurement for improving our model. And so we're going to get into this thing called gradient descent, which is an iterative learning process to reducing loss here. It's a little bit like a hot and cold guessing game. If you just take an initial guess at your parameters, b and w here, and then compute the loss, you could change your parameters for b and w to something else. So like, let's say I said that this is going to be 1 and 3/2. And I can compute my loss, and my loss was equal to 10. I'm just making up some numbers. So then if I change b and w, and I go to, let's say, 2 and, instead of 3/2, 2 and 2, and then my loss is equal to 8, this is better. And so this is closer to getting that 0 loss that we're trying to minimize. So it's kind of like a hot and cold game. If I'm going in the wrong direction, you know, if the loss gets worse, then I know maybe I'm going in the wrong direction. So here's this iterative approach to computing loss. We're going to take an initial guess, and then we're going to go ahead and compute that loss. Once we compute the loss, we're going to go ahead and adjust our weights. Once we adjust our weights, you compute the loss again, and you're going to repeat this process, hopefully reducing the loss over and over and over until your model converges. That would be that the loss stops changing or is changing extremely slowly. Okay, and there's a lot of details, like I said, there's a lot of details here in this iterative process. One detail that's worth mentioning is what's happening in this adjustment of weights. That in the middle here, we don't just have to take a hot, cold guessing approach. There's some magic that happens, and that magic is with gradient descent. And so we can use mathematics and the idea of derivatives, if you have a understanding of derivatives measuring the slope, telling you instantaneous rate of change and increasing, which direction you would go to increase. We can compute derivatives, partial derivatives, and gradients. And then when we do this adjustment, we don't have to do this hot, cold guessing comparison. We can know we're going to adjust in the best direction. So a little bit of a refresher on partial derivatives for you here in case it's been a while. Partial derivatives, if I have a function, let's say e to the 2y times sine of x, then the partial of f with respect to x, we just take the derivative there and we get to hold y constant. So if y is constant, e to the 2y is constant, and the derivative of sine is cosine. And we can take the partial of f with respect to y. We hold x constant. That means sine of x is constant, so we take the derivative of the exponential function. using the chain rule there, that's 2e to the 2y, and then times sine x, okay? So partial derivatives are used in the gradient. The gradient is the vector that points in the direction of the greatest increase of your function. This is great because when we get to doing something that has multiple input features, like this case up here, we're going to be dealing with multivariate functions. We're going to look at gradients. So the gradient is just the individual partials essentially in a vector. So the gradient of f of xy, the first component would be the partial of f with respect to x. The second component would be the partial of f with respect to y. So if f of xy was that same function, e to the 2y times sine x, then our gradient is e to the 2y cosine x, and then 2e to the 2y sine x. So you can evaluate this gradient at a specific point. So if for some reason this was coming from our loss function and we had initial guesses, let's say we started at 0, 0, if we evaluate our gradient at 0, 0, we see the output vector is 1, 0. And this tells us the direction of the greatest increase. So what we want to do then is we actually want to go in the opposite direction because we want to reduce our loss. So we calculate our gradient. Our gradient tells us which direction we go for the greatest increase, and we're going to go opposite in that direction here, okay? Again, in a later deep dive video, if you want to look at calculating the gradient here of your loss function, our gradient, our partial L with respect to W is negative 2 over n times the summation of xi times yi minus the y hats. And the gradient of L with respect to the intercept, or that bias term B, is negative 2 over n times the sum of yi minus y hat I. So with those gradients in just a simple linear regression model, what we do is you would take your existing coefficients and you would adjust them in that direction. So what you see over, what I have over here is W1. This is kind of like a recursive approach. You take your existing value here, and I'm going to go, oh, that looks terrible. Let's just get rid of that. I'm going to go W0 minus, because I want to go in the opposite direction of that greatest increase, H times partial L partial W. H is this thing called a step size, maybe, if you will, or alpha or learning rate. It's one of the parameters in gradient descent. And I'll adjust B1 in the same fashion. I'm going to take B sub 0, my initial guess. I'm going to adjust my weights based on the gradient, and that is my new guess, and I reiterate this process. I can compute the loss, adjust weights based on the new updated gradient, so on and so forth. This step size H is actually kind of interesting and something important here. On a simple 2D diagram to try to get a feel for this, this would maybe be my step size H here, okay? So if this was my starting point, my initial guess, and this is my value of my my weight W, then if I calculate the gradient, it's going to tell me to go to the left, so I'm going to go opposite. I'm going to go this way, a unit size of H, and then that is going to give me my next value for W. I'll calculate the gradient again, go the opposite direction. It's still to the right, and I go here. So the step size tells you how far over you're going to need to go here. It is possible to have a really large step size that goes too far, right? So if I have an extremely large step size, I'm going to overshoot, and I'm going to end up over here, right? So there's a couple of details that are really interesting about this. It turns out that linear regression problems that we're going to be looking at here are convex, which in one sense means if I overshoot the minimum, so our goal would be to find maybe the value right here. That's our goal, right? This is the holy grail spot. If I overshoot that, the next time I compute my gradient, it's just going to tell me to go that direction, which is kind of nice. But there's a lot of details in step size where you don't want to take too big of a step size because you don't want to keep going back and forth. And secondly, you don't want to take too small of a step size because then it'll take a long time to converge, right? If I only move this far and have to do that, I might have to do 10,000 iterations, whereas a slightly larger step size could converge more quickly. And there's some ideas and techniques to have this golden step size in your problem, which is not something we're going to worry about. We're just going to implement a step size variable and let us change it. But understanding what that step size is an interesting question in and of itself. So that is gradient descent and that iterative approach here. And then the converging process too is something we could implement later in our function if we want in coding, but we could also just implement it for a fixed number of steps, say, 1,000 steps or 10,000 iterations or something. And we can just keep track of the loss function. And if it's not changing much, we can essentially say that's going to converge, and kind of loosely saying. And if we wanted to go more into convergence, we could do that. Again, that's a whole nother deep dive. That's a really exciting thing to look at. Okay. So some of the equations and formulas we have here are good, but this is only going to work if we're doing simple linear regression. So we want to set this up so we can code and have multiple inputs. That's one of the nice things about Numpy is it's a really good linear algebra, really good with linear algebra and matrices and calculations and dot products. And this actually extends quite nicely in a pretty quick fashion. So instead of having just one predictor or one input x1, let's say we have something like we've got up to k predictors. So now I've got a linear regression model that I'm going to allow multiple inputs here, okay? And we're not even going to talk about feature selection or anything like that. This is just going to be about the linear regression process. So maybe you've done your data cleaning already. That's not something that's unimportant, but it's a separate topic. So we selected k features we want to input there, right? We can write this in matrix notation here as the product of an n by k matrix and a k by 1 matrix. I've got my w vector right here. So this is going to be like a w vector, and this is like a capital X. And so I can write this as y equals x dot w, and that will give us our predicted values. Notice this column of 1s here is that constant column to deal with that intercept or bias term w0. And in terms of extending the equations we had above into this general form, we end up with, if we use y hat as the vector of the observed values, the loss function looks like this. It is 1 over n w transpose times x transpose times x times w minus 2y transpose times x times w plus y transpose times y. And there's a couple weird things about going from the loss function in the case with just simple linear regression to vectorizing it to get here. So I encourage you, if you want to try this on your own, that's really cool. Some things to be aware of that I had to refresh myself was, in terms of looking at this loss function we had at the top, what happens to this summation here? One, if you have the dot product of two vectors, that is essentially going to replace the summation in our loss function when we do the dot product of two vectors there. So that's why there's no summation there. And then also another thing is that there's this transpose. I call this sock shoes property. I think I actually remember that from abstract algebra. But AB transpose is B transpose times A transpose. And so that's where you maybe kind of see this W transpose times X transpose stuff coming into play here. Another detail that's in the niche of making this calculation, which I'll have a stream or another 30-minute plus video on, is that the transpose of a scalar is equal to itself. And there's a lot of quantities in these calculations that end up being scalars, even though they don't look like it. For example, x times w, when you have your you're making a single prediction there. If you're doing a single prediction, you get a scalar, and so you can take the transpose of that. So things that don't necessarily look like scalars might end up being scalars if you just do the dimensions. X times w is not a scalar. That's a bad phrase. That's going to be an n by 1 matrix. But if you look at your dimensions here, there's a lot of things that actually end up being a 1 by 1 quantity, which in fact L here is a scalar, because that's just a single value. That's your loss function. The gradient of L, then, once you have this, the gradient of L, now you just want to take the derivative here with respect to W to get that. And the matrix calculus, the vector notations handles everything appropriately. You could look at this doing a little bit of like a product rule there. After some simplifying, 2 over n times x transpose times x times w minus x transpose times y. For coding, it's worth noting that you can factor the x transpose out on the left here and write it in this fashion. And that's useful because the quantity x times w is the predicted values. So now that I have the predicted values, that's going to be a quantity I can probably store when I'm coding, and that'll be easy to reference. So I can use my gradient to update my coefficients. And so I'm going to update my coefficients like I would here. I would just have a w vector, and I would subtract some step size times the gradient and update all my coefficients in that single array. All right, I think that's everything we need. Let's go ahead and get ready to code this up in Python.